So today we will discuss about design of brakes, right? So a brake is basically, it is defined as a mechanical device, right, which we are using for absorbing the energy possessed by a moving system, right? Because we are uh, taking any particular body which is in motion to rest with the help of brakes, right? So this is basically a mechanical device, right, which is absorbing energy, right? So it is, or it absorbs the energy possessed by any moving body, or we can say moving system or mechanism, right, by means of friction, right? So basically it will convert it to heat energy. So generally three main types of brakes are in use, as mechanical, hydraulic and electric, right? But we will focus on this mechanical brakes. Yeah, right. So and this brakes capacity is also an important characteristic, right? Whenever we are designing any brake, its capacity is also uh, uh, parameter which we need to have idea about how it is being decided. So basically it depends on the unit pressure between braking surfaces, right, and area which is in contact is also a parameter which affects the brake capacity, then radius of the brake drum as well as coefficient of friction. So these are all the factors which are going to affect the brake capacity, right? Now if we think about uh, the energy equations, right, then as we know that for linear motion as well as rotational motion, we are having uh, this kinetic energy, right, in both the case is given by this equations respectively, 1 half mv square as well as 1 half I omega square. So as brake is absorbing the energy of moving element, then the energy which is being absorbed by the brake can be given by this kinetic energy in case of this linear motion is 1 half m v1 square minus v2 square. So v1 is the velocity before the application of brake, and v2 is the velocity after the brake is applied, right? Similarly for rotational motion, this energy which is going to be absorbed by brake will be 1 half I omega 1 square minus omega 2 square, right? So this is how energy will be absorbed by the braking element. Sometimes it is this what we can say, some potential energy also sometimes may be the energy which is being absorbed by brake in case of hoists and all, right? What we are doing is we are absorbing the potential energy which is given by this mgh, right? So whatever energy we are transferring through brake is ultimately going to converted into that heat energy, right? And this total energy is represented by this mt into theta, where mt is the braking torque and theta is the angle turned, right, by the that particular drum while absorbing the energy, right. So this is how we are having various energy, right, or various energy transformations associated with the design of brakes, right. So with this simple understanding, you can attempt this question, which says a solid cast iron disc 1 meter in diameter and 0.2 meter thick is used as a flywheel. It is rotating at 350 rpm. It is brought to rest in 1.5 seconds by means of a brake. So calculate the energy absorbed by the brake and the torque capacity of the brake. So you can try this question. So first you can note down this given data, right, that diameter is 1 meter, then thickness is equal to 0.2 meter, right, then this rpm is given as 350 rpm, and time is given as 1.5 second. So what you need to calculate is energy absorbed by the brake and the torque capacity of brake. Sorry?
At first have to calculate the mass of the disc.
Yes,
Density into volume.
correct. Because while calculating this energy, you have to go by this equation, right? mk square is nothing but that moment of inertia only. So in order to have idea about the energy absorbed, you first have to have idea about this mass as well as radius of gyration. Omega 2 you can consider 0, right, and omega 1 you can calculate from the rpm 2 pi n by 60, 2 pi n 1 by 60. Now in order to calculate mass, so you have to have that density, right. So density of cast iron is not mentioned here, right. So density you can take as 7200 kg per meter cube, right. So once you have this, then you can calculate the mass, because you know the diameter, you know the thickness, right. So volume will be pi by 4 d square into t, and you have density also now, so you can calculate mass. Yes, correct?
Yes, sir.
Yeah. And here for the solid disk, that radius of gyration is provided as d by root 8, right. So your k square will be this d square by 8. Diameter is given as 1, so your k square will be 1 by 8 meter square. So can anybody tell what is the mass?
Sir, 1130.97 kg.
1130.97. Okay. So here,
Yes, sir.
yeah.
Same.
Okay, 1130, right, 0.97 kg. So once you have all this, I guess you can calculate energy now, right. You just need to plug in all this data. You have mass, you have radius.
95,033.
Sorry?
Energy is coming 95 kilojoules, sir.
Okay, but you should go by joule only. First tell me what is this omega 1? 2 pi n1 by 60.
36.65.
Okay.
36.5.
65 radian per
Okay.
second.
Okay.
Yes, sir.
Okay.
Same, sir.
Yeah, yeah, correct. So once you have all this, then keep it in joules only. This energy. Don't directly go for kilojoule. Then what will be your answer?
94946.8.
Okay. Right. So this will be your answer for energy. Right. Now what you need to do is you need to calculate the torque capacity. Right. So in order to have idea about the torque capacity, you know energy is equal to torque into the angle traversed, right? That theta which we have seen. E is equal to mt into theta. So now you have already calculated energy, right? You need to calculate theta first in order to have idea about the torque, right? So the theta is actually omega 1 plus omega 2 by 2, right, into this thickness, right? So with this you can calculate theta. Omega 2 is 0, omega 1 you have already calculated. So
Sir, sir,
yes,
if we do it by angular acceleration alpha, I alpha.
I alpha, but we don't have alpha, right, with
Oh, yeah.
us. Okay,
Yes.
so for
Uh,
now we need to go by this only.
but yeah, we can calculate alpha as well. Okay, thank you, sir.
If it is provided you can go by that also. So what is theta?
27.48.
27.48 almost. Okay, so now you can
What is
calculate
T, sir?
this empty.
What is, excuse me, sir, what is T?
T is thickness. Sorry, T is time. Sorry, T is time. So it has come from that omega is equal to theta by t, right? D omega is equal to d theta by dt. So from that theta is equal to omega into t. Okay. Hello.
Yes, sir.
So here it is 1.5
Okay, sir.
second. Sorry, I first told thickness. Actually it is time. So now tell me what is torque?
3454 Newton meter.
It is almost coming about 3454, right? So 3454. Okay, so this is how you can calculate this torque and energy absorbed in braking applications. So in block brake, as you can see, the construction is like this shown in this particular figure. So in that we are having a lever on which block is mounted, which is going to resist the motion of that rotating drum, right? And in this particular figure, this free body diagram shows the various forces acting on a different component, right? So as you can see here, the force acting is this particular force, right, mu, and that is the frictional force, right? And the distance, or this is also this frictional force, this mu n, right? And the distance is this radius of this drum. So in this case the braking torque is given by this frictional force into the distance, which is this radius of this brake drum, right? And this particular force, this normal force, is defined by the pressure acting on that normal force into the cross section, which is this length into width, right? So this length and width of block is considered here in order to calculate the normal force, and braking torque is given by this frictional force into that radius of the drum. Now there are two cases for this block brake. When this the length of this, or sorry, the width of the block is short and width of the block is long. It means if this block is going to subtend an angle which is less than 45, right, if this angle is less than 45, then it is going to be considered as short block, right? So first, if we go for this, then actually when we are considering this short block, then it is also considered as that this is 1/4 of this diameter of this brake drum, right? And so width is going to lie between this dimensions, 1/4 of the diameter of brake drum and the half of the diameter of brake drum. So when width of block lies between this, you can consider it as short block. Now in this, if you see this forces, if you see, then it can be balanced by this Rx, which is in horizontal direction, is being balanced by this frictional force, right? Here this Rx is balanced by this frictional force. Similarly, we are having this vertical force Ry, which is going to be balanced by this particular normal force, right, minus this particular force P, right? So this is how you can have equilibrium of forces, right? So up to this it is clear? Yes or no?
Yes, son.
Right. Now if you take moment, sigma of moment about point, or this fulcrum point O, or this pivot O is equal to 0, then the moment generated by the force P and this frictional force is in anti-clockwise direction, right? Both this also and this also, right? While the moment generated by this particular force N is in clockwise direction. Is it clear?
Yes, son.
So if we consider this anti-clockwise moment as positive, then P cross B plus this mu N cross A minus this N into, sorry, here mu N into C is there. A is the distance for that force N, right? So here mu N into C and N into A is equal to 0. So once you have this equilibrium, then from this particular equilibrium you can have this force P, right, which can be represented with this A minus mu C, right, divided by B into N, right? You can simplify this to this. Is it okay?
Yes, son.
Now once you have this particular equation, then you can have idea that in which particular condition you need to provide the external force in order to stop the drum, right? So if you see this equation, then you are having three different cases right here, case 1, 2 and 3. Let us see. So first case is your this distance A is greater than this mu into C. So if A is greater than mu into C, it means you need to provide some external force, right? External force, right, in order to stop the drum, right? So this is the case where external force is required, right? Similarly, when A is equal to mu C, then you need not to provide any force, right? So the self-locking condition start from this. Without providing any force, your this particular drum is locked, right? It is not going to have any motion, right? Similarly, if A is less than mu C, then also you will have this negative p, right? So it is also uncontrollable conditions, right? Because you have no control with the help of this external force applied on your this particular block, right? So when this a is less than or equal to mu c, it is not desirable condition, right? Because there is no force, there is no role of this external force p in this braking operation, right? So this is how for this simple short block brake we are having this condition for self locking. Now one more important thing is, here we have assumed that the rotation is clockwise, right? While carrying out this analysis, what we have assumed is this clockwise rotation of drum, right? If it is anti-clockwise, right, as it is mentioned in this particular figure, if it is anti-clockwise, then this force will be given by this a plus mu c upon b into n, right? So this again you can derive by considering all these forces acting and taking equilibrium of forces and equilibrium of moment, right? So up to this it is clear. Hello.
Yes, sir.
Okay, so once you have idea about this, then you can go with this simple numerical, I guess, in which it is mentioned that a single block brake with a torque capacity of 250 Newton meter is shown in this figure. The brake drum rotates at 100 rpm and the coefficient of friction is 0.35. Now calculate the actuating force and the hinge pin reaction for clockwise rotation of the drum. Okay, then the actuating force and hinge pin reaction for anti-clockwise rotation of the drum. Okay, then the rate of heat generation during the braking action, right? So let us go for this particular calculation, and I guess some whole thing is there but I missed it. So we will calculate up to this third point, right? So let us see how you are going to calculate this. So can you try this one? Hello.
Yes, sir.
Okay.
Yeah.
Yes, sir.
So first you need to calculate the first you need to note down the given data. That is, this torque is given as 250 Newton meter, right? Then n is 100 rpm, mu is given as 0.35, then this pressure is mentioned as 1 Newton per mm square. So pressure is not mentioned in this, but in the last point they have asked to find the dimension of block, right? And in that they have mentioned that this pressure intensity is 1 Newton per mm square, right? And the length of block is twice the width. Length of block is twice the width, right? So in the last point they have asked to find the dimension at the dimensions of the block. Yes, so these are the given data. So I guess first you need to draw this free body diagram, right, for both the cases. clockwise and anti-clockwise. Right, if we go for this, then here you are having this this will be your frictional force, and this is normal force. Similarly here also you will have this normal force and frictional force, right? So here the force is applied at Ry and Rx. You can consider like this. Correct? Is it correct? For clockwise
Yes, sir.
direction,
Yes.
you will have
Yes,
this
sir.
forces acting, right? So once you have this data with you, you can go for taking moment about this fulcrum. But before that, as you know that this mt is given by this mu n into r. So from this first you can calculate this n. Correct?
Yes, sir.
Yeah. So what will be your n? mt is given as 250 Newton into mm. If we convert, then it is 250 by 10 raised to 3. 250 into 10 raised to 3. Mu is given as 0.35, and this radius is given as 200. So your n will be
3571.42.
3571.42 Newton. That will be your n. Now you can take moment about the hinge pin. Right, this may be your hinge pin. So you are given all the distances, right? So if you take moment about this hinge, then your mu n is acting at a distance of 50, right? Mu n is acting at a distance of 50, and it is anti-clockwise, right? Here this is anti-clockwise, for this p also anti-clockwise. So p into 500. This can be equated to this n into 200, because n is producing clockwise. Is it correct? Yes or no?
Yes, sir.
So this will give you the force P. So what is P?
Is it 1303.57?
Yes, so this is coming as 1303.57 Newton. Now once you have this, then you can calculate this Rx as mu n and Ry as n minus P. So you have mu, you have n, right? So what is this Rx?
One 1,251.
Okay, it is almost around this 1251 Newton. Similarly, you have n and p, so Ry will be
2,267.8
right.
Newton.
So 2267.8 Newton almost. So this will give you then reaction, right? Rx square plus Ry square. So what will be this R? that is
2589.96.
2589.96 Newton, right? So now once you have calculated this, you can also calculate it for the this anti-clockwise rotation, right? So for anti-clockwise rotation, I am not again drawing the figure, but as you know, what is going to happen is this friction is going to change the direction, so it will be minus mu n into 50, right, plus p into 500 will be equal to that n into 200. So this will again give you this p around 1553.57 Newton, right? Are you getting the same?
Yes, sir.
Okay, so once you have this particular p, then again you can calculate that Rx and Ry. Rx is not going to change, it will remain that 1251 or almost 1251 Newton. Ry is going to change because this p has changed, right? So it will come around this 2017.86 Newton almost. So this will again give you that new reaction, that is Rx square plus Ry square. So it will be around 2373 almost. So are you getting the same?
Yes, sir.
Okay. Now these are the first two things, right? For clockwise rotation and anti-clockwise rotation, you need to calculate these reactions. So the next was you need to calculate the heat generated, right? So how can you calculate the heat generated? With that frictional force into average velocity, right? That will give you that energy, right? So rate of heat generated is nothing but this frictional force into average velocity. So first you need to calculate the average velocity, right? How you will calculate that average velocity?
Pi n d by 60.
Sorry?
Pi n d by 60.
Uh,
u1 plus v2 by 2.
Actually you need to consider that both velocity, right? So final velocity and initial velocity, and then you need to take average, right? So if you go for that average velocity, then it is initial plus final divided by 2. So basically that velocity is nothing but omega into r, right? So omega is 2 pi n by 60 into r, whatever is given. N is given as 100 and r is 0.2, correct?
Yes, sir.
Yes, sir.
So from this 2.094 meter per second, correct? So it will come as 1.047 meter per second. So once you have this average velocity, then you need to simply put it here, because this frictional force is mu n and this average velocity you have calculated. So it will give you this rate of heat generated. So what is it?
1308.9.
It is almost 1308 Newton meter per second, right? Or whatever. The last is the dimension of block. So here if you go for this dimension, So what is this dimensions of block? How you are going to calculate this? As you know, this normal force is calculated with this, right? N is equal to P L W. We have seen this, right? Yes or no?
Yes, sir.
So from this, you know, pressure is given as 1, L is given as 2 times width, right? So here you can have this N is equal to 2 width square. So you can calculate width from this because you know N. So what is width?
42.26 mm.
Okay, if it is 42.26, you can consider it as 45 mm. So from this length will be 90 because length is 2 times width. Right. Now whether this block is self-locking or not, can any one of you check this? How will you check it first? Do you know self-locking?
If P is coming negative, then self-locking.
That is correct. That is one way, but which parameter we have considered for
Moment.
this? That is also correct, but in the final equation of P, which parameter we are checking in order to decide whether brake is self-locking or not?
A minus B.
A and mu.
Yeah, so you need to check this A minus mu C is equal to what? A is 200 mm, mu is 0.35, C is 50, right? So is equal to what?
So it is not self-locking.
It is not self-locking because here some positive number will come, right? So A by C is greater than mu, so brake is not self-locking, correct?
Yes, sir.
Okay, so now
So does self-locking signifies self-energizing?
no, self-energizing is totally different than self-locking. Self-energizing means your frictional force is helping your this external effort in stopping your drum. That is self-energizing. Okay.
Okay, sir.
Okay. So now let us go further. Right, that is this particular this block with long shoe. Right. So in case of this block with long shoe, we cannot go for that assumption that directly that normal load is acting equally on the full block. So that is why they have considered this particular small element, this RD5, and for that this Tn is being considered. So in this long shoe brake, what you need to do is you need to consider this Dn, right, as this pressure into that area. Previously we were directly taking that L into W, but here L will be the length of this arc, which can be given by this RD5 because length of arc is that radius into theta. So this length into still we need to consider the width as we were considering previously also, right? So for this particular case of long shoe, this Dn is defined by this pressure into RD5 into W. Now as this is this normal force, then this frictional force will be defined as this mu Dn, right? So that is mu RD5 this W into this pressure, right? Similarly, your this torque or braking torque is given by this mu n into R. So this will be this mu R square d5 W into this P. So this is how this MT can be represented as this mu R square W, this P to d5, right? So this is how this braking torque is defined in this particular case with long shoe, right? Now if we consider the wear in this particular friction lining of this kind of this long shoe brake, then from this particular figure you can consider that as this is delta y, this is delta phi, sorry, this is phi only, right, and this is delta r. So from this you can write that this delta r is equal to delta y cos phi, right. So which gives you that delta y is equal to delta r upon cos phi. So delta y and delta r is actually amount of wear across this delta r is across the radial direction, delta y is this vertical wear. So it is having this relation between them, right. Now this delta r, which is this wear along the radial direction, is proportional to this particular force mu dn, right. So if you further elaborate on this, then this dn we have defined as mu r d phi into w, this is area, right, into this pressure. So from this you can write that this delta r is actually proportional to p, right. So here in place of delta r you can write p actually, right. So what it will give is this p by this cos phi is equal to constant. So from this and this relation what you can write is p by cos phi is equal to constant, right. Now from this if you take it further, then this is p is equal to c1 cos phi, right. Now for phi is equal to 0 it is maximum, right, p is equal to p maximum. So it will give you c1 is equal to p max if you put this phi is equal to 0. Then this equation can be modified as p is equal to p max cos phi, right. Now what you can do is you can replace that p with p max cos phi in the equation of that normal force dn which we have defined earlier. So this dn can then be written as this r d phi into w, which is area, into this p max cos phi, right. So this is further can be calculated by integrating this dn cos phi, right. So if you put the value of this dn and if you give full if you further simplify by integrating it, what you are going to get is, I am not going for full integration, I am directly writing that you will get this rw p max 4 theta plus 2 sin 2 theta, right. So actually further you can simplify this as 1 by 2 rw p max as this 2 theta plus sin 2 theta, right. Now once you have calculated this n, then if you are going to put that p is equal to p max cos phi in the equation of your braking torque also, then it can be mentioned as with this mu r square w p max, this minus theta to plus theta, your cos phi d phi, right. Here also it is minus theta to plus theta only, right. 1 second. So yeah, if you simplify this, so if you simplify this then again you will come up with this mu r square w p max into 2 sin theta. Now if you write it in terms of that n, right, that 1 by 2 r w p max into 2 theta plus sin 2 theta, if you put this value into this empty, right, or you simplify it to write it in terms of that n, then what can you write is this mu n r 4 sine theta upon 2 theta plus sine 2 theta, right? So finally you can write it as mu dash and r, right? Mu dash is this equivalent coefficient of friction, right, which can be represented with the multiplication of this term and this term, right? So this is how you will get this particular mu dash, right, when you are considering long shoe. So with this particular explanation about this long shoe, then we can go to this band break, right? In band break, actually you are having this construction as mentioned here. The load is applied, you will have this a particular band which is wrapping to drum. So you will have a tight side and slack side. As you know, in this build drive we are having tight side and slack side, so you will have this tight side and slack side, right? And if you draw the free body diagram of forces acting, then there will be this kind of forces acting on this particular lever as it is mentioned here, right? So in band break, if you go for this equilibrium of forces, right, then and equilibrium of that moment, then if you take moment about this particular point, right, or this hinge joint, then you can write that this P2 into A, because this is the distance and this is the force, right? So this P2 into A is equal to this P into L, right? So you can write this P in terms of this P2A by L, right? And as you know, in this belt drive, this tension in tight side and slack side is represented with this relation P1 by P2 is equal to e raised to mu theta. Is it correct?
Yes, sir.
Right. So once you have this basic idea, right, then if you can see the forces acting, right, in a particular portion of this d phi as it is mentioned here, right, so you can come up with this dn again as this p into that rw d phi, right, as we have seen earlier. Also here also it is like this only, right? Now if you go for equilibrium of forces, then this dn is opposed by this p into sine d phi by 2, right? P into sine d phi by 2 is acting here downward, right, component. Similarly here also a component acting downward as p plus dp sine d phi by 2. So opposite to this dn, these two components are acting. So from that we can write this dn is equal to p sine d phi by 2 plus this p plus dp sine d phi by 2. As we know, this d phi is very small. This sine d phi by 2 itself can be represented with this d phi by 2 only, right? And if you put this d phi by 2 into the above equation, then your this dn can be presented as this p d phi by 2 plus p d phi by 2. We are neglecting this dp into d phi by 2 because it will be very small quantity, right? So here basically this is p d phi, right? So from this dn is equal to this p d phi, you can have your this particular pressure is equal to this force upon Rw. If you write this relation into the above equation of the Tn is equal to the PR W d phi, then you will find that this pressure is coming as this force upon this radius into width, right? So this is how you are having this relation in case of this bend brake, right? So this is simple bend brake, whatever we have seen, right? There is one more type of bend brake, that is this differential bend brake, right? So if you see this differential bend brake, then in that case if you take moment about this fulcrum, then you will have this P into L, which is having this clockwise movement. Similarly, this P1 into B, it is also having clockwise movement, right? And this P2 will be having anti-clockwise movement. So one of them can be positive and negative, right? So if you take anti-clockwise positive, then clockwise negative, and if you take clockwise positive, then anti-clockwise negative, right? So from this you can write your this effort which is required can be given by this P2A minus P1B divided by L. Now here also, if you further simplify it, then you know that P1 is given as P2 e raised to mu theta. So if you take this P2A minus P1 as P2 e raised to mu theta, right? Then it will give you this P2A minus P e raised to mu theta divided by L, right? So this is how this braking effort is calculated in this differential band brake. So here also, if someone asks you to write the condition for self-locking, then can anyone tell what will be the condition for self-locking?
A equal to B e to the power mu theta.
Sorry, A,
Equal to B mu theta.
right? So this A equal to B e raised to mu theta, or actually in order to avoid this particular condition, your A should be greater than this B e raised to mu theta, right? So if in case this A by B is less than or equal to e raised to mu theta, then self-locking is there. Is it correct? Yes or no?
No, sir, it is not self-locking.
सर आपने बताया था कि ए अगर छोटा हो जाएगा तो मतलब इशू हो जाएगा ना, फिर नॉन कंट्रोलेबल हो जाएगा.
Yeah, so that is self-locking. That is what I am telling. If this A by B is less than or equal to this e raised to mu theta, then there will be self-locking, because then your P will be coming negative, na? So in order to avoid this self-locking, this A by B should be greater than e raised to mu theta. Are you getting what I am saying?
Yes, sir.
Yes, sir.
Correct. So basically this A needs to be greater than B e raised to mu theta in order to avoid self-locking. Yes or no?
Sir, in the previous case, you told that A equal to mu C is the condition for the self-locking.
Yeah, it means it is whether it is equal to or less
Less
than.
than.
In both case, it will be self-locking, uncontrollable also if P is going negative. But basically, the desirable condition is A should be greater than e raised to mu theta. In that case, the operator needs to provide a certain amount of effort in order to apply the brake, right?
Okay, sir.
So the desirable condition is this A must be greater than this B e raised to mu theta. Then only certain amount of effort is required in order to stop the drum which is rotating. Correct? Are you getting?
Yes, sir.
Right. So after this idea, you can try this one.
Sir,
Yes.
can we go to previous slide where delta, del R and del Y came into picture?
I guess here only, huh?
What is del R and what is del Y?
It is basically wear, as it is mentioned here. This is wear, right, which is taking place because of this forces acting in this particular brake shoe, right? So this delta y is in vertical direction and delta r is along the radial direction.
Means it is a weird particle or weird layer.
It is wearing means that particle will come off or torn off from that particular braking surface, sorry, from that frictional surface which is providing the braking action.
Okay, means it is having thickness del R and del
Ha,
Y
ha.
it's
Which
vertical.
is which is getting worn out, right? We are assuming that.
Okay.
Ha, ha.
And phi, sir?
Phi is
Phi.
this angle, as here we have considered.
And whether this is a short break or a long.
This is long break only, as we have I guess already considered here, right? We are talking about long break only. It means long shoe only, right? Block.
Okay.
Huh.
So that's why we are integrating with respect to d phi.
Yes, yes, yes.
Okay, sir.
Okay. So minus theta to theta we are integrating, right? Okay. So
Okay.
now if we go for this numerical, I guess you will be able to solve this. Let us go quickly. That a differential band break is shown in this figure. Now the width and thickness of the steel band are 100 mm and 3 mm respectively, and the maximum tensile stress in the band is 50 Newton per mm square. The coefficient of friction between the friction lining and the brake drum is 0.25. Now calculate the tension in the band, actuating force, and the torque capacity of the brake, and find out whether the brake is self-locking. You can try this one, right? Yes or no?
Yes, sir.
Yeah, it is
Sir,
simple.
I mean that the maximum tensile stress is this is allowable or this is present in the present situation.
Maximum tensile stress in the bend, it is I guess which is present I guess, right? Because it is mentioned that it is there. So maximum tensile stress in the bend is 50 Newton per mm square. So it is actually the present tension. Okay.
Okay.
Yeah. So which will allow you to calculate the force, because stress is provided and you have area with you. Okay.
Yes, sir.
So if you first note down the given data, then the width is 100 mm, thickness is 3 mm, and the mu is 0.25, sigma t is 50 Newton per mm square, r is 300 mm. Yeah, so from this first you can calculate the P1, right? The tension in the this band, which is given with this stress into area, W into T. So straight away you can calculate this 50 into 100 into 3. Yes, correct?
Yes, sir. 15,000 Newton.
15,000 Newton. So once you have this, you can calculate P2 is equal to P1 upon e raised to mu theta. Now theta you need to convert into radian, right, by multiplying it with pi by 180. So this is basically this 15,000 divided by this e raised to mu is given as 0.25 into theta is pi by 180 into 240, which is the angle of wrap given, right? So now this P2 will be what?
5292.87 Newton.
5292. हाँ
सर 263 आ रहा है मेरा तो.
हाँ. Actually it is coming 263 only, 5263 only, right? it is almost 5263 Newton. Right, I guess 2.718 or in that some calculation may be varied, right? So all of you almost are getting this 5263.
Yes,
I'm
sir.
getting 5265.
Okay, that is okay. Right, now actuating force you have to calculate by applying that equilibrium of moment. So if you apply that equilibrium of moment about this particular fulcrum, then what is that? This P1 into 50, right? So this P1 into 50 plus this P into 950, right? Because this both will have positive, right? Yeah, this will have this clockwise, here this will have this clockwise moment, and then this will be negative, right, anti-clockwise. So this will be P2 into 200 is equal to 0, right? So if you go for this, then you will find P is equal to, you have the values of P1 and P2, so you can calculate this P.
Yes, sir. 318.7 Newton.
Okay, it is almost 318.7 Newton. So now once you have this, then torque capacity can be calculated in this band brake. Is here braking torque is given by this P1 minus P2 into R. So this also can be calculated, you have all the data with you. So can anyone tell me quickly?
29 lakh 21,100 Newton mm.
2921.1 Newton meter almost. Now finally self-locking condition, whether the brake is self-locking or not. We need to calculate A by B and e raised to v theta. So for self-locking, A by B must be less than or equal to e raised to mu theta. So calculate both, what is A by B and what is e raised to mu theta.
So since value of P we have calculated is positive, so it is not self-locking.
Correct, that is also a correct interpretation. Yes, the brake is not self-locking, but still you can show this value here also. What are these values? A by B and e raised to mu theta. A by B is 4, right?
Yes, sir.
And e raised to mu theta is
2.85.
2.85 almost, right? Okay, so this is how we have answered this, what they have asked. So up to here it is clear.
Yes, sir.
So if we go for the next one, then let us see some of the questions from GATE. So in a bend brake, the ratio of tight side and tension to the slack side of the tension is 3. P1 by P2 is 3. The angle of rep on the bend drum is 180. So whatever angle you need to convert it into radian, right? So pi by 180. Now the coefficient of friction between the drum, you need to calculate this. So it can be done, right? So what is
Point three five
point?
35.
Okay, let me check. Yes, every one of you are getting this 0.35.
Yes, sir.
Okay, because it is simple, right? This P1 by P2 is equal to e raised to mu theta. This 3 is equal to e raised to mu into pi, right? So basically this
Sir,
yes, ln
सर इन द केस ऑफ ब्लॉक ब्रेक विद लॉन्ग शू उसमें सर केवल जो टॉर्क कैपेसिटी उसका फॉर्मूला याद करने से हो जाएगा
sorry.
या द इक्वेशन ऑफ द torque capacity in the case of block brake with long shoe
Hmm.
by learning only the torque capacity formula it will work or full derivation will be needed मतलब इस तरह के क्वेश्चन आएंगे क्या
See, actually in GATE they are not asking derivation, but sometimes if you have idea about how it is derived, then if you forget the exact equation, then also if you have enough time, you can derive over there itself, right? So better to go with at least understanding how that particular formula has come up, right? So if you
ओके
see the derivation, then it can help you if you have time, right? Because it may happen that if you remember all those equations, sometimes you may not be confident that whatever you are writing is correct or not. So in that case you can verify whatever you are writing is correct or not by deriving then and that itself. Okay.
ओके
Yeah, so this ln3 is equal to mu pi will give you this mu is equal to almost 0.35, right? So after this, let us go to this one now. In this, a band brake consists of a lever attached to one end of the band. The other end of the band is fixed to the ground. The wheel has a radius of 200 mm and the wrap angle of the band is 270 degree. The braking force applied to the lever is limited to 100 Newton and the coefficient of friction between the band and the wheel is 0.5. No other information is provided. Okay, then the maximum tension that can generate the band during the that can be generated in the band during the braking and the maximum wheel torque that can be completely braked is. So can you try this particular question? Hello.
Yes, sir.
Yeah, so here this theta is given as 270 degree, mu is given as 0.5. So here please mute yourself. So here if you
सर इन
sorry,
कुछ नहीं सर हो गया
Sir, in equation of self-locking, what is A and what which side to take B?
so in self-locking actually okay, for this then this particular distance and this differential bandwidth, yeah, as you can see now here in this tight side is given as this A and slack side is given as B, correct?
No, tight slide is
Tight,
B. Na?
sorry,
Tight side is B. Na?
tight side is B, yeah, yes, and then slack side is this A, correct, right?
Yes.
Now you can go here, yeah. So the maximum tension,
सर इन विच डायरेक्शन इज द ड्रम मूविंग सर
one second. They have not provided, I guess, any information. So in that case, what you can do is you can assume that it is moving in this direction only, right?
So sir, the answer can be either 18.95 or 2110.
So 2110 is the correct answer, right? Because if you take this moment about this particular point, right, or hinge, right, then what will happen is in this tight side, if this force is acting in this direction, then this T into 1 will be equated to this 100 into 2, right, which will give you this T as 200 Newton, correct?
Yes sir.
Right. So, and after that, if you apply this T1 by T2 is equal to e raised to mu theta, right, where mu is 0.5 and theta is given as 270, which is 3 pi by 2. So e raised to 0.5 into 3 pi by 2, right? So your this is T2 actually, right? Then you will find your T1. In that case, I guess this direction needs to be assumed this way. So this T1 you are getting as 2110 Newton, correct?
Yes sir.
So once you have this, then braking torque, just now we have discussed how you are
Three,
calculating
yes.
braking torque in case of this band brake. T1 minus T2 into R.
382.
382, yes, it is T1 minus T2 into R, right? If you put all the value, R is given as 0.2, so if you put all the values, it will come around 382 Newton. Okay, so now if you go for the next one, then here block brake shown below has face width of 300 mm, mean coefficient of friction is 0.25, for an activating force of 400 Newton, the braking torque in Newton meter. So can you try this one?
Yes sir.
So please go ahead and try. You can take moment about A, right? In order to find the N.
45.
Yeah, 45 is the correct answer. But first you need to show that this sigma of moment about A is equal to 0, right? Since you are considering this point as this fulcrum point. So in that case,
सर फॉर विच एंगल ऑफ कांटेक्ट जैसे एक्सीड करेगा तो वो लॉन्ग शू माना जाएगा.
uh, you need to go for greater than 45. Here it is provided exactly 45, right? So we are not going for that particular calculation of that mu dash, right?
ओके सर.
Yeah. So
Sir, is it applicable?
sorry,
45 degree.
no,
Is
for
it
45 degree we can go with that short only. Okay,
okay, sir.
so this n into 200, right, where n is going to be applied at this point, right? So this n into 200 can be equated with this 400 into 600, right? So from this you can first calculate n. So it will be around 1200 Newton. So once you have this, then frictional force can be mu into n. So mu is given as 0.25 into 1200 will be 300 Newton. So once you have frictional force, then braking torque will be this frictional force into radius. Radius is given as 150 mm. So this 300 into 0.15 will give you 45 Newton meter. Is it correct?
Yes, sir.
So now if you go to the next one, then a force of 400 Newton is applied to the brake drum of 0.5 meter diameter in a band brake system as shown in the figure. Now where the wrapping angle is 180 degree, the coefficient of friction between the drum and the band is 0.25, the braking torque applied in Newton meter. So can you calculate this? Hello.
Yes.
So
Yes, sir.
what you need to do is you need to calculate T1 and T2, right? So T1 is provided as 400 Newton, right? Because here you will have this T1, right, which is equal to this 400 Newton. So here you will have then this T2, right? But you calculate T2 from the T1 by T2 is equal to e raised to mu theta. Theta is pi only, right? Mu is given as 0.25. T1 is there, so you can directly calculate T2. What is T2?
Sir,
400.25
B, sir. 2.3.
into pi. What is T2?
189 कुछ है सर.
182 point
हाँ,
192.64.
182.375 almost. Okay, then what is this torque? T1
54 point.
minus T2.
54.4.
Yeah, so this MT is equal to T1 minus T2 into R. R is given as 0.5 meter by 2, right? That is 0.25. So it is 0.25. You have calculated T1 and T2, right? If you put all this value, then MT will come as 54.4. Now the next is a drum brake is shown in the figure. The drum is rotating in anti-clockwise direction. The coefficient of friction between drum and shoe is 0.2. The dimensions shown in the figure are in mm. The braking torque in Newton meter for the brake shoe is. So here also you can calculate. So here also if you take moment about this fulcrum, then you will first find this relation between this frictional force and Rn, right? Because you don't know friction force as well as that normal force both, right? So here it is this Rn, and this will be mu Rn. See here, this frictional force is considered as acting on this particular block, right? Because you may have that confusion that this wheel is moving in this direction and frictional force is also in this direction. Actually, if this wheel is moving in this direction, then this block is assumed to is moving in the opposite direction, and then this frictional force is moving opposite to that. So it is clear to you, right?
Yes.
Yeah, so this Rn and mu Rn having this direction, you can take this sigma moment about this O is equal to 0. So this 1000 into 800 will generate this anti-clockwise, right? And this both will have clockwise, mu Rn as well as this Rn, both will have clockwise. So this mu Rn into 100, right?
Yes, sir.
Plus this Rn into 480, right? Correct? So this will give you relation between this frictional force and Rn.
So mu rn into 100 will be minus, no, sir?
No, mu r into 100 is also plus, because I have changed the direction, means taken both the force in the opposite side of this anti-clockwise moment. So I have equated this anti-clockwise moment to both this clockwise moment. Are you getting? Hello? Are you getting this? Hello?
No, sir. Mu rn and 1000 will cause the moment in anti-clockwise, no, sir?
No, this mu rn is causing in clockwise, no? It is in this direction. So it is causing this clockwise. This n is causing anti-clockwise.
Okay, sir.
Again
Got
this
it.
Rn is causing clockwise. So I have equated anti-clockwise to clockwise. Right? So I guess from this you can calculate Rn, because you have mu with you, right?
1600, sir.
1600 Newton. So once you have this Rn, you can calculate frictional force mu Rn is equal to what? 0.2 into this, right? Because mu is 0.2, so it is 320 Newton, correct?
Yes,
Yes,
sir.
sir.
And then braking torque will be equal to this frictional force into drum radius. So drum radius is again 200 mm, means 0.2 meter. So 320 into 0.2, so you will have 64 Newton meter,
64.
right? Because this is 0.2. FF you have already calculated, so 64, correct?
Yes, sir.
Okay.
Yes.
So now let us go for this. A single block brake with a short shoe and torque capacity of 250 Newton meter is shown. The cylindrical brake drum rotates anticlockwise at 100 rpm and the coefficient of friction is 0.25. The value of A in mm, right, such that the maximum actuating load is 2000. You can calculate this, I guess it is simple. Yes or no?
Yes, sir.
So quickly calculate this. See, this braking torque is given, right? So this is nothing but this frictional force into this radius, correct? So this 250 can be equated to this 0.25 into Rn into A, right? And now if you take the equilibrium of this particular forces, sorry, if you take equilibrium of moment about this particular fulcrum O, then what are the forces acting? This is having anti-clockwise motion, right? It is mentioned here, anti-clockwise. So here also both of these forces, as in previous case, this mu Rn as well as this Rn, both will have clockwise and this P will have anti-clockwise. So this P into 2.5A can be equated to this mu Rn into A by 4 plus this Rn into A. Yes or no?
Yes.
So from this uh, you can calculate, I guess, because here you are having Rn in terms of A, right? I guess Rn is 1000 by A. Yes or no?
Yes, sir.
Right. So you can put this Rn in terms of 1000 by A, and then you can simplify in order to get P. Actually P is provided, right, anyway. So you need to calculate the distance, actually A, sorry.
Yes, P is
Sir,
2000 here.
Sorry, P is 2000 given. So if I
sir,
write P as 2000, actually let me write P as 2000.
212.50.
One second, 2000 into 2.5 into A. Mu is what? 0.25. Rn is 1000 by A, so 1000 by 4 here, and here directly 1000. Right, if you solve this, you will find A. So what is A?
A is equal to 212.50.
Yeah, it is 212.5 mm. All of you are getting this?
yes, sir.
Okay, okay. Now, yes, next is a short shoe. External brake is shown in the figure. Diameter of the brake drum is 500. A is this, B is C is this. Coefficient of friction. All of the things are provided, right? The drum is rotating anti-clockwise, taking drum. I guess you can do this, right? It is simple only, right?
Thanks.
All the data are provided, right?
Yes. Fine.
Yeah, so you can first take this moment about O equals to 0, right? So here again this mu n and n will have this direction, right? So you can have this F into A is equal to, now actually in this case this mu n will help this braking torque, right? Because it is this particular anti-clockwise, and here also it will come anti-clockwise because fulcrum is below this particular block or this frictional force. Okay, are you getting what I'm saying?
Yes, sir. Yes, sir.
So here it is plus mu n into A, right? Mu n into A equals to n into
Okay.
B, right? You are having all the data with you, so you can calculate n. F is given as 100, A is given as 1000,
सर म्यू एन इंटू सी होगा ना.
mu is 30.35 into n into A is, sorry, yeah, here it will
सर
be
सी
C.
आएगा ना,
Yeah,
म्यू एन इंटू सी.
yes, 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 correct. Yes, 0.35 into n into C, which is 200, equals to n into B, that is 500. So this will give you n. What is n?
Two 32.56.
Yeah, it is almost 232.56 Newton. So once you have n, you can calculate the braking torque as mu n into this radius of drum, right? This braking torque mt can be this mu n into r. You have mu 0.35 n, you have calculated. R is given as 250 mm because diameter is 500.
सर ब्रेकिंग टॉर्क इज 20.3392.
It is almost 20.35 Newton meter. right? 20.35. So all of you are getting this?
Yes, sir.
Okay, then if we go for the last one, here a short shoe drum brake is shown in the figure. A force of 1 kilonewton is applied to the lever. The coefficient of friction is 0.4. Now the magnitude of the torque applied by the brake is, again you can take the moment about fulcrum, right? This fulcrum O. So it is very simple. Here the direction is clockwise, right? So your mu Rn will be in this direction, Rn will be in this direction. So if you take moment about O, then this particular 1000 Newton into 1000, right? Distance is 1000. This is generating this clockwise, right? Then this particular mu Rn will be anti-clockwise. Similarly, this Rn is also anti-clockwise, so this can both be taken on the other side, right? So what is mu? Mu is given as 0.4, right? So mu is 0.4 Rn into this distance is given as directly not given, right? It is given as this radius and this 310, so this distance is given as 310 minus 260, correct?
Yes, sir.
Right, so this 310 minus 260 plus this Rn into 500, right? If you solve this, you will find Rn, correct?
1923.
Yeah, it is almost around 1923 Newton. So once you have this Rn, you can calculate frictional force as mu Rn. So what is that? Mu is given as 0.4. So what is Fr, or whatever this frictional force Ff? What is this?
769.231.
769.61 Newton almost.
231.
So this empty braking torque is Ff,
200.
Ff into radius of the drum. So it is almost coming around 200 Newton meter, right? So this 200 will be your answer, correct? Okay.
Yes, sir.
So today we are
Yes.
keeping it up to here.